Okay, so we're going to finish up section 4.5 tonight. And then really 4.5 is also designed to help us with section 5.10, which deals with what are called improper integrals. That material then, I mean, we'll cover that on Thursday. Okay, very important section. All right, let me give you a moment to copy this example down, and then we'll talk about it. Okay, so wow, look at this problem. We're taking the limit as x approaches 0 from the right of the function 1 plus the sine of 4x raised to the power of the cotangent of x. Okay, so let's see here. Okay, so I'm going to take the limit as x approaches 0 from the right. Well, let me just ask you this. Hold on. The 1 plus the sine of 4x. Okay, what does this approach as x approaches 0 from the right? What does 1 plus the sine of 4x approach?
1.
Good. That's right, Anshin. It approaches 1. Because the 4x, that's right, Sandhya, good. 4x approaches 0. So, I mean, well, if I even want to be more clear here, let me just write this like this. 1 plus the sine of 4x approaches 1 plus the sine of 4 times 0 as x approaches 0. And 4 times 0 is 0, and the sine of 0 is 0, so this means 1. So 1 plus the sine of 4x approaches 1 as x approaches 0. Now let's talk about the cotangent of x. Okay, let me just kind of separate this out here. Cotangent of x is the cosine of x over the sine of x, right? So what does the cotangent of x approach as x approaches 0 from the right? That's right.
Oh, it's plus.
What do you get there, Ange?
Infinity on the positive side.
Well, and by the way, the cotangent of x is also 1 over the tangent of x. And so indeed, the tangent of x approaches infinity. Well, wait, no, the tangent of x approaches 0 as x goes to 0, and 1 over 0 would approach infinity. So this is indeed correct. And you're correct. You have the cotangent of x approaching infinity as x approaches 0. want to be a little from the right. It would be indeed would be one moment. Yeah, it would be positive infinity. So this function here now, this function 1 plus the sine of 4x raised to the cotangent of x power acts like 1 to the infinity power. So you have a power approaching infinity, and then you have a base 1 plus the sine of 4x that approaches 1. That's an indeterminate form, 1 to the infinity power. Because remember, you're approaching 1 and you're raising it to the infinity power, but how you're approaching 1, how does the 1 plus the sine of 4x approach 1? It's very important. Okay, so because, like, for instance, just as an example, if you had 0.9, well, no. What matters is how the rate at which 1 plus the sine of 4x is approaching 1, along with the rate at which the cotangent of x is approaching infinity. You see, you have these two functions that are, in a sense, you need to know how their rates at which they're approaching their respective limits. So how are we going to handle this problem? Well, here's what we're going to do. We want to find this limit. And what I'm going to do is I'm going to let the variable y, I'm going to make a substitution here, not in like an integration sense, but I'm going to make a helpful substitution. I'm going to let 1 plus the sine of 4x raised to the cotangent of x power, I'm going to let that equal y. I'm going to let that equal the variable y. And then what I'm going to do is I'm going to take the natural log of y. Okay, so I'm going to sort of digress here, and instead of looking at how my function y behaves as x goes to 0 from the right, I'm going to study how the log of y behaves as x goes to 0 from the right. And this is going to be very helpful. You'll see why. Okay, so now why do I want to worry about the log of y? Well, it's because when I take the natural log has some nice properties in it. And one of the properties of the natural log is that if I take the natural log of a to the bth power, that equals b times the natural log of a. See, that power, that cotangent of x there, that power is making this a very difficult limit, making it a difficult limit to work with. So I'm going to say, well, let me study the natural log of y. And if I do that, the natural log of my function will equal then the cotangent of x times the natural log of 1 plus the sine of 4x. You notice I'm keeping the limit there. The limit as x goes to 0 with the problem, because I'm not taking the natural log yet, right? I mean, I'm not taking the limit yet. So okay. Now what we have is, I have this cotangent of x times the natural log of 1 plus the sine of 4x. That's what I have, right? But I need a ratio of two functions, not a product of two functions. And it has been noted that the cotangent of x is the same as 1 over the tangent of x. So that puts then the tangent of x, here in the denominator. And then, of course, you still have the log of 1 plus the sine of 4x in the numerator. So this is my f in the numerator, and the tangent of x is my g in the denominator. And now, what do we know that, well, the log of 1 plus the sine of 4x as x approaches 0 would approach the log of 1, right? What's the natural log of 1? 0. That's right. Good, Sandia. And the tangent of x as x approaches 0, that's going to approach the tangent of 0. Tangent of 0 equals what? That equals 0. Good. So now you have an indeterminate form. You have 0 over 0. And you can therefore apply that L'Hopital's rule. So L'Hopital's rule says that the limit as x approaches 0 of f over g is the same as the limit as x approaches 0 of f prime over g prime. So f prime is right here. Had to use the chain rule. You had 3 functions there, right? For the chain rule, you had to use 3 functions. The log, the 1 plus the sine of 4x and the 4x. So there's the derivative of that numerator. And then the derivative of tangent is secant squared. So there's g prime. Now what we can do is there's no, yeah, well, I mean, I can just take 0 now since the denominator is not equal to 0 of this new expression, f prime over g prime. I can just substitute in 0 everywhere I see an x. Okay, so this would be, I mean, if I were to put in an additional step, this would equal the limit as x approaches 0 from the right of 1 over 1 plus the sine of 4 times 0 and I know it's going to get a little bit bunched up here, times the cosine of 4 times 0 times 4. All of that, right? You're going to have all of this here over the secant squared of 0. That's your denominator. But secant of 0 is the same as 1 over the cosine of 0. And so secant squared then would just be 1 squared. So I'm hopefully you understand how I have all these values here. Sandia, the cotangent of x, I wrote the cotangent of x as 1 over the tangent of x here. Okay, So I'm not interested. I mean, the derivative of the cotangent of x is not involved in this problem. All right. Okay, very good, very good. So we end up getting 4. We end up getting 4. Now that's not our answer. That's not our answer. Let me see. And she's asking a question. We're not done yet. Not done yet, but let's see here. Well, so Mario, because of that cotangent of x as it's a power, then you use the natural log to help you. Anytime you have a function raised to a power, to a function that you have a function that's raised to, like if you have like f of x, or let me do, like if you have you have a function, say h of x, and you're raising it to the power j of x, you're going to be taking the log of that function. Okay, you're going to be taking the log of all of this. So that's like in your homework for section 4.5. Anytime you have a function that's raised to a power and the power is itself a function, you'll take the natural log of that. Okay, is that all right, Mario? And the limits are going to be okay, you know, that they, so now look at what we have here. We have the limit as x approaches 0 from the right of the log of y. Mario, if you have any questions on that, see me after class, okay? Are you feeling a little more comfortable? Okay, very good, very good. Good question. This is what we have. This is our result. But I'm interested in how just the y function behaves as x approaches 0 from the right. So how can I get to the y function based off of the natural log of y? How can I get there? What do I have to do? If I have a limit about the natural log of y, and I wanted to learn about the limit of the y, of the function y, how can I get from the natural log of y to the function y?
Exponential.
Exponentiate. That's right. Good, Ange. Good. So on the next page, I mean, we do it. So the 1 plus the sine of 4x raised to the cotangent of x power, that's equal to y. That was what y is equal to. But y itself, I can write y as e to the natural log of y. But we already know that as x approaches 0, the natural log of y approaches 4. And so the answer is going to be e to the 4th. That's the limit. And that's not something you could easily get, like, for instance, using Desmos, if you were to do a graph. It's not something you could easily get. You want to be using the L'Hopital's rule to help you find your limits. I mean, there's no way Desmos would, you know, give you e to the 4th. It would give you a decimal, right? But Webb assigned one simplified radical form. That's right. That's right. Sandia, e raised to the natural log of y is equal to y. But we know that as x goes to 0, the natural log of y approaches 4. And so you get e to the 4th power. Please let me know if you have any questions. That's correct. Hold on here. Right, that's right. Good, Sandia, that's right. How many are feeling comfortable? Are we comfortable with this? Taj is good. Nathaniel's good. Okay. Sandia's good. All right, great, great. Well, if there are no questions, I'll stop the recording. Javier's good. Excellent, excellent. Okay, I'll stop the recording.